I will not explain the relation, but I think you learned quantum mechanics and the concept of Hamiltonian. In that case, the Hamiltonian is an operator or matrix. Here, the classical mechanics, Hamiltonian is just energy, number. Okay. But if you know the energy, Hamiltonian, you can write the equation of motion. In quantum mechanics, Hamiltonian is energy, and energy is a matrix. And to find the solution of the equation of motion in the quantum mechanics, what will you do? Isn't it, in general, Hamiltonian is off diagonal. I think it does, I don't know. I mean, maybe I will not go, because if I start to talk, it's going another direction. Its point is that you learn the school that the diagonalization of the Hamiltonian, to make everything diagonal, to find the rotation, or the transformation, and diagonalizing. Then you can solve them. Actually, this is a classical diagonalization. It's corresponding thing. Originally, there was a coordinate, and then by the transformation, you eliminate the coordinate by transformation. Then you can solve it. In the classical mechanics, in that case, after you diagonalize, isn't it, each diagonal element becomes invariant of motion in quantum mechanics. Here, same. After you eliminate the coordinate, you have invariant of motion. Then you can solve the problem. Okay. Now, so this is already I explained a lot of the important things. Now, for the preparation, let me see. I will not prove it, but this is the, from the point of, look, in the phase space, there was a trajectory. And to solve the problem means you find one point, go to next point, next point, next point. This kind of the point goes to next point is called point transformation. Point goes to point. And this is also point transformation. Canonical transformation is a point transformation. Because first you have this set of the point. Now map to the another set of point. So that means when you try to solve the dynamics, one method is that you follow the point transformation. But there is another way to see the problem, same problem, is you consider some function, set of the points. Then time going on, each point, this means it's a certain probability this has this point, this point, this point. Then how it will change. You see, there is a bunch of the set of the point is here, and there is no another point. Then you ask how this will change in time. Okay? So not point, but area. But this can be described another way, is that, say, this is a phase coordinate. You have originally this distribution function. This is the initial condition. But time going on, this distribution function change to like this way. So that case, you are not asking how each point to move it, but how, as a result of the background motion, the function of the probability to find this function move, change in time. So, therefore, there's two different views. One is a point transformation. Another is how function change in time. It's a complementary view. And both is very important view. And when we describe the dynamics, this view, there is a very, what kind of the dynamics exist. Suppose, you see, you have, it's called ensemble of the points. And you have the distribution function you see, before this Hamilton equation of motion, that case, xi is a function of time. Okay? But when we say this function, this is a function means this point is fixed. So this is not a function of time. But the form of the function change in time. But point is simply here. Never change. So therefore, don't mix up. Okay? That case, we are trying to find trajectory dynamics, point transformation, x, y, x, and p are function of time. But when we go to the description by the change of the function, now x, this is called phase function. And this quantity obey some dynamics. So suppose that is the case, that is the point follow the Hamilton equation of motion, we know, but I will not write it down, okay, this way. Hamiltonian is given. This is an equation. If point transformation is a Hamilton equation of motion, distribution function of the point obey this equation. You see again Hamiltonian obey. This is a partial differential equation. That is a usual ordinary differential equation. This is a partial differential equation. And this equation is called Liouville equation. And actually, when we talk about the dynamics, there is completely two different views and complementary views. And one Hamilton equation of motion, another is a Liouville equation, and both are the fundamental law of physics, the most fundamental equation.